or in the 420 20? Anyone? You can just put up your hand. Okay, I see only 1, 2, 3, and the rest have taken it a while ago, I suppose. Okay, 4. Okay, 5. Okay, so all right. Okay, so most of you have taken it. Okay, good. So let's look at pure bending. Okay, so if you have a beam that is simply supported, okay, so over here you have a pin, and over here you have a roller, okay, and then we have a load. The load over here coming down is known as P, and the distance from here to here is L/2, and the distance from here to here is also L/2. Okay, and then we have 3 points. I'm going to label them as point A. Then we have point B, and we have point C. So point B is where the load is applied. Okay, so if you look at the free body diagram, or sorry, if you look at this structure which is simply supported, and then we are going to draw our transformation. This is X, and this is Y, and this is rotation about Z. Okay, so if you were to analyze any structures, you have to draw your transformation first. Okay, to tell the audience which is your X direction, which is your Y, and your rotation about Z. Okay, so what you see over here on this side, you have a pin, right? And then on the other side is what we call a roller support. Right. So if you were to look at motion or position, okay, we know that X, okay, so if or sorry, if you look at the travel, okay, the degree of freedom, right, X must be equal to 0, Y is equal to 0. Means at point A, we don't allow movement about the X and Y direction. Okay. Whereas when it's in a roller, right, X is not equal to 0. So we allowed it to go what? Left and right. All right. We allowed it to go left and right. Whereas Y is equal to 0. Okay. So anything that we restrict motion has a reaction. Okay. So with movement restriction, there is a reaction. Okay. So what do I mean by that? So if we were to construct our free body diagram, okay, if we were to construct our free body diagram, right, so what we have, okay, so this is our point A, point B, and this is our point C, and we know that we have a load P over here. So what we have over here, right, so we will have a AY, and we also have a what? AX, right? And at point C, we only have a what? CY. Why we only have a CY? Because we restrict motion in the Y, but in the X, it can go what? Left and right. Okay, so that's why there's no CX at point C. Okay, so this is how you will draw your free body diagram. Okay, so now this topic that we're talking about is in bending moment. Okay, so I'm going to write down the general formula for you. Okay, so what we have is stress X, right, is equal to minus mz over IZZ multiplied by Y. So this is one of the formula that we're going to use for bending moment. Okay, where you have stress X is in the X direction is equal to minus MZ over IZZ multiplied by Y. So some of you will ask me, Eugene, what is stress X? Okay, so if I were to take an element, okay, so I'm going to take an element, or I'll take a small position. Okay, so this is my element. Okay, and if I were to draw this element, okay, so over here, I take the element, okay, I'm going to draw it. Okay, so this is our element. I want you all to get used to terms like element, okay? So what we have over here, right? So over here, this direction is our stress X direction, okay? So it's going to follow this transformation, okay? And then if we have Y, this is our stress Y. And then if we have our shear, this is our shear XY. Don't worry about the shear first, okay? And shear YX, okay? So that's our shear forces, okay? So our bending will induce, okay? So our bending moment the bending moment will induce stress in the X direction. Okay, for this case, okay, we're going to see stress in the X direction. Okay, so let me define what is in that term. Okay, so stress X is stress X is defined as the normal stress in the X direction. Okay, and the units can be Pascal or PSI. Okay, then we have MZ. So MZ is moment about the z-axis. Can be Newton, meter, pound, inch. Okay, and then you have IZZ, which is the second moment of area about the z-axis. Okay, so the units down here can be meter to power 4 or inches to power 4. And then Y over here is the distance from the geometric centroid. Okay, and again, this is in meters or this can be inches. Okay, anyone, any questions so far? Anyone? Okay, so I don't hear anything, so it's okay. So a good thing I want you to observe. So I'm going to call this equation 1. Okay, is to observe the minus sign down here. Okay, now before I go on to elaborate about this minus sign, what we are doing over here, so equation 1 is to calculate the normal stress or stress X distribution. Okay, I want to highlight down here This is a distribution that we are calculating. Okay, so probably doing 2p, right? You'll derive the equation. Okay, I'm not going to derive it, but I want you all to observe something over here. Okay, there's a minus sign over there. Okay, and how does this work? Why is there a minus sign? Why is not stress x is equal to mz over izz multiplied by y? Okay, why do we have to have a minus sign over there? Okay, so to do that, I'm going to look at the deformation pattern. Okay, we're going to look at the deformation pattern. Okay, so anyone, any question? No. Okay, so let's look at the deformation pattern. Okay, so we're still using the same loading, simply supported with a point load at point B. Okay, so we are going to look at the deformation pattern now. Okay, so deformation pattern. Okay, so deformation pattern is how the structure will bend, right? So with this, we know that the structure will bend in a smiling face like this. Okay, so this is how the structure will bend. Let me move it across. I need it to be lower. Do apologize. All right. So this is where our point A is, our point B, and our point C. Okay. Then I'm going to sketch the centroid. So the pink line where you see, this is known as our centroid. Okay. And then I'm going to label the point over here. Now, question for you. If this structure were to fail, where is it going to fail? Anyone? I'll repeat again. If this structure were to fail, okay, or I'll show you guys this. Where is it going to fail? Anyone, please? I have no answer. Are you still there? Hello? Yes, point B. Thank you. So failure will occur at point B, right? So that is why when we calculate the stresses, we will tend to calculate where failure will occur. Okay, we don't need to calculate the stresses at point A or point C. It's point B that we're interested. Okay, so at point B, I'm going to label the top part. Okay, so this is our point B. Okay, so right, I'm going to draw a line across, and over here is my point alpha. Over here will be beta. Okay, so we know that the structure has gone through a moment at point A and at point C. So the moment will look like this. I'm going to draw the moment vector now. Okay. Right. So MZ and MZ prime, that is the couple. This is how the structure will deform. Right. So can anyone tell me at point alpha, will it be tensile or compression, please? Anyone?
Compression.
Compression. Okay. So why is it compression? Because you have a smaller circumference. Yes or no? Okay. So over here, you will go through compression. And on the outside, you go in tensile. Okay. And if we were to draw our transformation again, okay, so this is our transformation. X and y, right? Rotation about z. So just to clarify, why is it the